8.3 finds special products of polynomials. The diagram to the right shows a square with a side length of a plus b. The area of the square is then represented by a plus b squared. Now, to the right here, we can cut this big square into 4 smaller shapes. One would be this big square here, so the area would just then be a times a, and the other small square would be b times b, which is b squared. And we would get 2 rectangles that are the same. So the length of this rectangle is a, and the width will be b, a times b. And the same goes for the other one. A times b makes a times b. So then we can write the area of the square as a squared plus ab plus ab plus b squared, which then makes a squared plus 2ab plus b squared. And now we get this pattern, which we call the square of a binomial pattern. Whenever you get a binomial that's squared, you can immediately expand this squared binomial as a squared plus 2ab plus b squared. And for this case, when you have a subtraction sign in between, it will be a squared minus 2ab plus b squared. And as to why this is subtraction, I will leave it for you to think about. Okay, we're going to look at an example here. First, to expand the first binomial, you can take x squared plus 2 times x again times 8. And then we're going to add that to 8 squared. So again, the x squared will represent the a squared here. 2 times x times 8 will represent 2ab, and then 8 squared will be your b squared. And then your signs are still positive. Okay, so you pay attention to that. And then now, x squared plus 16x plus 64. And the same thing will go for another one with the subtraction sign for the binomial. X squared minus 2 times x times 7 plus 7 squared. So the x squared will be your a squared here, followed by the subtraction sign, and then 2ab, 2 times a times b, and then your b squared with the addition sign in between. Okay, now we can further simplify this as x squared minus 14x plus 49. Okay, now we're going to look at the sum and difference pattern. So by the FOIL method, I can expand this as a squared minus ab in the inner plus ab and the outer minus b squared. Now I can cancel out the middle to get a squared minus b squared. So whenever you get a binomial that's multiplied together and the first numbers are the same and the last numbers are also the same, then you can simply take the square of the first number and subtract the square of the second number. So the example to the right here, we have the sum and difference pattern, m minus 6 and m plus 6. So we could take m, square it, take 6, square it, and put a subtraction sign in between. And then we could further simplify this to be m squared minus 36. Okay, now we're going to practice a few problems using the square of a binomial. So for this first one here, we look at the first term of this binomial and we square it. And then we're going to have to take 2 and multiply it to the first term, 3m, and then to the second term, n, and then square n. And then we can further simplify this as 9m squared plus 6mn plus n squared. And then for this next one, we're going to have to look at negative x squared. Because it's a subtraction sign in between, I'm going to put a subtraction sign here. And then I'm going to have to take 2 and multiply it to the first term, negative x. And I'm going to multiply this to 2y. Notice I did not take the negative or subtraction sign here and put it next to 2y because I already considered that here. And then I square 2y. And then I'm going to further simplify this to be x squared plus, because negative makes positive, and then 2 times 2 makes 4x y here, and then 2y squared makes 4y squared. Okay, now for the next two examples, we're going to apply the sum and difference pattern to find the product. Okay, so as you noticed, the terms are the same, and we have a subtraction sign and a plus sign. So I'm going to take 9, square it. I'm going to take 4t, I'm going to square it and put a subtraction sign in between. So this will be 81 minus 16t squared. The next one, same thing. It doesn't matter if the plus sign is first or the subtraction sign is first. So I'm going to take 3m, square it, subtract 11n squared. You can further simplify this to be 9m squared minus 121n squared. Okay? And then the next one, use special products to find the product of 26 and 34. Now, I'm not going to have you directly use the ordinary algorithm to solve this. Instead, I want you to think about, like, you can take 26 and rewrite it as 30 minus 4. You can take 34 and rewrite it as 30 plus 4. In this case, we can use the sum and difference pattern. So 30, we can square that, subtract 4, and we can square that. And this makes 900 minus 16, which makes 884. And then in the bottom, we want to perform the indicated operation using the functions f of x equals 4x plus 0.5 and g of x equals 4x minus 0.5. And for the first one, they would like you to take the product of these two functions. So I'm going to go ahead and substitute in the functions for its binomials. Because they have the same terms, we can go ahead and use the sum and difference pattern, and that would be 4x squared minus 0.5 squared, and this will make 16x squared minus 0.25, and that's it. In the next one, we're going to have to take f of x squared. So basically this expression, 4x plus 0.5, and we square it. Now we're going to have to use the square of a binomial to expand this. So I'm going to take 4x, I'm going to square this, and I'm going to take 2 times 4x times 0.5 plus 0.5 squared. And this will make 16x squared. And 2 and 0.5 cancels out. So this will be 4x plus 0.25. Okay, let's take a look at this word problem. The color of the dark patches of a border collie's coat is determined by a combination of two genes. An offspring inherits one path color gene from each parent. Each parent has two color genes, and one is black and the other is red. And the offspring has an equal chance of inheriting either one. So we want to say this is 50%, this is also 50%. And the same would go with the other parent, 50%, 0.5. Okay, and the gene B is for black patches and the gene R is for red. Any gene combinations with a big B results in black patches. Suppose each parent has the same gene combination, BR. The Punnett square shows the possible gene combinations of the offspring and the resulting patch color. So if we look at this Punnett square here, this offspring will definitely get a black color, okay? And the big B and the little r, this offspring will also get a black color because the big B is actually called what we call the dominant gene. It will cover up the recessive gene, the little r, meaning the color is hidden. So we also have another one here, big B, little r. So this offspring also must be black. And this offspring has to be red because there is no dominant gene here. Okay, both strands of genes are both red. So in part A, it asks you, what percent of the possible gene combinations of the offspring result in black patches? So I listed all the possible combinations. There are 4 in all, and 3 of them tells us that the offsprings will definitely be black. So we just take 3 and divide by 4 to get 0.75, multiply by the 100 to be 75%. Part B asks you to show how you can use a polynomial to model the possible gene combinations of the offspring. So to model the gene from each parent, as I said earlier, there's a 50% chance of getting a B strand and a 0.5 chance of getting an R strand. So I would say to write this as a variable expression, you can take 0.5, multiply by B, and add 0.5 and multiply by the little r, the lowercase r. Okay, so this representing 50%. The same goes for this one. So there's an equal chance that the collie inherits a black or red gene from each parent. So the possible genes of the offspring can be modeled by 0.5 big B plus 0.5 little r squared, which is also the area of the Punnett square. So now we're going to expand the model. Okay, so then you get 0.25 b squared plus, we can cancel this out, and this would be 0.5 br plus 0.25 r squared. Okay, and to further explain this, 0.25 will just represent 25% black patches. I mean border collies with black patches, and 50% would also represent black border collies with black patches, and 25% would represent border collies with red patches. And we can total these up, the BB and the BR, to be 75%. So this is from part A. Now, part C asks you, what percent of the possible gene combinations of the offspring result in red patches? So we have it here, 25% of the possible gene combinations results in 25%. Okay, and this concludes the lesson.